Alright guys, in our first video on linearization, we looked at the relationship between the radius of a circle and the circumference of a circle. That is automatically a linear relationship, so when we graphed the radius on the x-axis and the circumference on the y-axis, we ended up with a straight line and a positive slope and a y-intercept of 0, showing us that our circumference and our radius are directly proportional. And when we calculated the slope of that line, we got a value very, very close to pi because, as we know, the relevant equation there is that the circumference equals 2 pi r. So I apologize, that circumference was the slope was very, very close to 2 pi, not pi. All right, so here we have another set of data involving circles, and here we're looking at the relationship between the radius of a circle and the area of that circle. And if we graph this data, what we will see is that we do not get a linear relationship, and you may know that if you know the equation for the area of the circle. But let's go ahead and graph that just to be sure. Alright guys, so as we can see, when I graph my area versus my radius, I get a graph that is concave up. And if you think about it, that's not surprising at all because our relevant equation that relates the area of a circle to its radius is A equals pi r squared. So when I graph area versus radius, it should not be linear. It should be concave up like a parabola. If I want to linearize my data, what I actually need to do is graph the area still on the y-axis, but my radius squared on the x-axis. And when I do that, I should get a straight line, and the ideal value of the slope of that line is pi. So let's see how that works out for us. Alright, so here I have my original data written out with my radius and my areas, and now what I've done is I've taken each value of my radius and I've squared it. And when I graph that, I expect it to be linear, and due to my relevant equation, A equals pi r squared. When I compare that to y equals mx plus b, what I can see is that if I graph the area on the y-axis, the radius squared on the x-axis, then my slope should give me an experimental value of pi, and I should get a y-intercept of 0. So I'm going to graph that. Let's see how it works. Alright, so I've created new and appropriate scale for my radius squared axis. I've redrawn my area axis, and I have plotted my points. And I can look at those points, and they appear to be pretty linear. So we're going to draw a line of best fit. So now I've drawn my line of best fit, and I can see that those points fit my straight line pretty well. And now what I'm going to do is I'm going to circle 2 points that are on my line, but not, I repeat, not data points. Okay, so I'm going to use this point right here where r squared equals 5, and it looks like at that point my area would be about 16, so that would be the point 5, 16. And then I'm going to also pick this point right here where my r squared is 20. And that appears to be a value of about 63 for my area. And so now when I calculate the slope of that line, that should give me an experimental value for pi. So we'll do that on the next page. Alright, so my points were 20, 63, and 5, 16. So now I'm just going to calculate my slope. So my slope is going to be my 63 minus 16 divided by 20 minus 5. And that comes out to 47 over 15. And if you put that in the calculator, round it to 2 decimal places, it comes out to 3.13. Now typically we need to have units on a slope, but in this case the correct units is not to have units at all, because if you look at what we're dividing our area in centimeters squared by our radius squared, which is also in centimeters squared. So centimeters squared divided by centimeters squared the units completely cancel out. Pi is something we call just a ratio. Ratios are always unitless, okay? So 3.13 would be our experimental value for pi. So now that we have an experimental value, we can do a percent error because we know that pi rounded to 2 decimal places should be 3.14. So we're very close to the correct value, but not quite. So let's do that percent error calculation. All right, so we calculate percent error by taking the correct value minus our experimental value divided by the accepted value and multiplying by 100. And that comes out to 0.32%. A lot of people like to do percent errors as an absolute value, which is fine. If we did not want to do that, technically we were below the correct answer, so we could say that our error was negative 0.32%, showing that we were low by 0.32%, but a lot of people just do absolute values on those as well. All right, so let's review the steps for linearizing motion, especially if you have data that's not linear originally. All right, guys, so the steps you're going to follow is first we're going to see what data have we been given or what data have we collected in a lab. And for the example we did today, that data was area and radius. And then we have to say, do I already know a relevant equation? Now, normally these would be equations that you've learned in physics. For example, we've just learned the kinematic equations. But in this case, the equation that is relevant, the equation that relates these two variables, is area equals pi r squared. So then we have to figure out, okay then, according to that equation, would my data be linear, or do I need to manipulate something? And since area is a function of radius squared, what I can see is that if I just graph area and radius, it's not going to be linear. I need to square the radius value. So in our example, we squared our radius. And then finally, once you make the graph and calculate the slope, you can figure out the ideal value of the slope by comparing to your y equals mx plus b to your relevant equation. So y equals mx plus b, a equals pi r squared. So we graphed our area on the y, we graphed our radius squared on the x, our slope should equal pi, and our y-intercept should be 0 because there's no plus anything on this equation. Now, let's say that you had decided to graph your radius squared on the y and your area on the x. That would actually be okay, but you're going to have to do a little something here. So if you do that, solve for radius squared, and you'll see that radius squared equals 1 over pi times your area. So if I compare that to y equals mx plus b, what I can see is if I do my radius squared on the y-axis and my area on the x-axis, then my slope would not be pi. My slope should actually be the reciprocal of pi. So then when I calculated my slope, I'd have to take its reciprocal to get my experimental value of pi. And that is completely fine. It just adds an extra step you have to do. All right, guys, so I hope that made sense to you. And tomorrow we're going to apply this concept to do a lab using the kinematic equations.